This is my Machine Learning Foundations for Product Managers project for Duke University's Pratt School of Engineering. My name is Richard Cavisto. The project overview. My task was to build a machine learning model to predict the energy output of a combined cycle power plant. I was provided 9,568 observations, which included temperature, ambient pressure, relative humidity, and the exhaust vacuum. In addition to the data set included, the actual power output for each observation was part of that. The objective here is to determine the machine learning approach. I need to decide on the model to use, select the features to use, and identify the appropriate algorithm to use. Using the data set provided, I need to determine if I use a straight holdout method, breaking down the data into a training, validation, and testing set, or use a cross-validation method such as k-fold cross-validation. Using the training data, I will run at least 2 models, but maybe more, and compare their performance. Lastly, based on the results, I'll select the model and figure out which one performs best. So first thing I wanted to do is look at the data. I thought starting here and trying to visualize the data sometimes helps. So I plotted them very simply. And you can see there is a little bit of a linear model to them. So therefore, I am likely going to go with a multiple linear regression model approach. So I decided to go with data splitting by choosing the 80-10-10 split instead of cross-validation. I'm making my work simpler while still achieving a solid evaluation structure. Cross-validation can sometimes be overkill. So an 80-10-10 split gives me the boundaries between the training data and the testing and validation data, making it easier to analyze the model's performance on the unseen data. I think multiple linear regression makes sense. It just seems like a logical choice. It's easy to interpret, it's efficient, so I will decide to go with that. I decided to test different feature sets which can reveal which variables contribute most significantly to the model's predictions. By experimenting with multiple feature combinations, it may highlight multicollinearity, which is where features are highly correlated with each other. This can sometimes inflate coefficients and skew results. So by iterating on feature sets, I may be able to pinpoint a combination that balances predictive power and stability. I decided to use MAE, MAPE, and R-squared. Each of these metrics will give me distinct insights into the model performance, which can be particularly valuable in understanding not only the model's accuracy, but also the nature of the errors. So MAE gives me the average absolute difference between predicted and actual values, which makes it highly interpretable in terms of the original target units. This makes it easy to understand how far off predictions are on average. Unlike mean squared error, which penalizes large errors more heavily, MAE treats all errors equally, which can be advantageous if outliers are not a major concern. So MAPE, of course, gives us the percentage, which helps when trying to understand the error in relation to the actual value. MAPE can also make results a little more digestible, but it can be more sensitive if there are 0 or no 0 values, but my quick review of the data didn't really highlight that, so therefore it makes sense. R-squared indicates the proportion of the variance in the target variable that can be explained by the model's features. It's valuable because it reflects how well the model accounts for the overall pattern in the data, although it doesn't directly quantify the error size. This suggests that, high values of this can suggest that my model explains most of the target's variability, meaning the features chosen likely capture the core relationship to the data. While it's useful, it's worth noting that it sometimes give you a false sense of security, especially if outliers are influencing the model fit. By combining these, I'm covering a range of perspectives: the absolute error, the relative error, and the model fit. This combination of metrics will allow me to be more informed, allow me to make more informed decisions and potentially tweak the features or explore some other paths. So here are the models that I ran. As you can see, the one in the upper left here, this is with all the features. And as you can see, the R squared is 92 and the MAE is 3.6 and 79.73. So I decided to take a couple out. These are the ones that seem to have the most connection, but the R squared went down while the MAPE went up. And you can look at the other four where I used just one variable. All of these, the values are a little worse, right? So the adjusted square, or the R squared is lower, and MAPE is higher, which is not a good thing. So therefore, I've decided to go with the first one, which is using all four variables. Here's the run of the model for the four variables, and you can see the output here. You can see the R squared is at 92%, which is really good. However, MAPE is high. It should be a little bit lower. So let's see here. So again, the 3.6, this value indicates the average error of the model's predictions in absolute terms. A lower MAE is typically better. However, 3.6 does seem good. 80% for MAPE. This is relatively high. It should be around 20 to 30%. So I don't love it, but they're all consistent. This is really the best, so that's why I went with this one. It could be because there's extreme values that could inflate the MAPE significantly. If I had more time, I would try analyzing if certain outliers are causing this spike. But I like the results, and so I ran the results against my final set, and again, it looks good. And so I think this is the model that I think works for me. Thank you.